We started talking about acid and bases in this chapter. So we talked about really the definition of an acid and the definition of a base. Remember, really an acid is anything that can produce H plus or H3O plus ions in solution. That is really your basic definition of an acid, is really that liberation of H plus or H3O plus, while a base is really anything that can produce hydroxide ions in solution. As we touched upon, I think last time as well, it's also a very good thing to keep in mind that if you see an equation and you see hydroxide on the product side, you're probably dealing with a basic type of situation. Well, obviously, if you see H plus or H3O plus in the equation there on the product side, it should definitely be a acid type situation. And that's going to be very helpful a little later on in this chapter with certain types of calculations. Now, we talked about a little bit more general definition of an acid and base, which is the Bronsted-Lowry definition, where an acid is a proton donor and a base is a proton acceptor. And the result of this, as we talked about, does create acid conjugate base pairs and base conjugate acid pairs, where you have a general form of an acid plus a base, regular old run-of-the-mill acid and base on the left-hand side of the arrow, your conjugate partners on the other side, where you have the conjugate acid and the conjugate base. The relationship is the acid on the left-hand side, its partner on the right-hand side is the conjugate base. And obviously the base on the left-hand side there, its partner on the right-hand side is the conjugate acid. The important thing is, as we talked about, pretty much we're talking really about a donation of just one H plus always. And that's really what ties these guys together. The only difference that there can be in order for them to be related to each other has to be only one H plus. In the case of an acid, because it's going to be donating the H plus, the conjugate base will have one less H plus. And in the case of the base, it's going to be accepting the H plus, which means the conjugate acid will have one more H plus, essentially the acid donating the H plus over there. That is, how you could kind of determine, if you'll have a conjugate acid or a conjugate base, if they are related to each other, again, by just that one H plus difference. As we saw in a couple of examples, if there's anything more than one H plus difference, then they are technically not related to each other. They're not partners in that situation. We talked about, I think at the very end, again, something like a diprotic acid, which has two hydrogens that come off, like sulfuric acid. They actually do come off one at a time, the hydrogens. So it's sort of a stepwise process. And that is why, as we talked about, I think at the end last time, something like H2SO4, it is a partner with what happens when it loses one H plus. So these two guys are partners. And really the next step that occurs is that guy that already lost an H plus will continue to lose one more H plus. And that again is why this guy and this guy are partners. But going from H2SO4 directly to SO4 2 minus is sort of a double jump there in terms of hydrogens. And those guys are not related to each other in the sense of conjugate acid base pairs. Clearly they're related to each other, but not in the sense of being pairs to one another. Any questions on that stuff that we talked about? Now, sometimes remember that you are not always told what you are dealing with, but you may be asked to give the conjugate acid or give the conjugate base. So understanding this relationship here can really help you. Again, if you're told you want to solve for the conjugate base, all you have to do is think backwards and go, obviously the partner would be the acid. So what I am looking at is an acid, and I should take off the H plus, and vice versa. Obviously, if you're asked to give the conjugate acid, you could kind of work your way backwards and see that what you're dealing with is actually a base. and you should put on the H plus. The other important thing is it is an H plus, so the hydrogen changes, but the plus also changes the charge that's associated with the conjugate guy. So you got to take that into account when you're adjusting it. Any questions on any of that? Okay, then we will continue on. We also talked about the idea of things being able to act as an acid or a base. Those are things that are amphoteric. A lot of times things that have a hydrogen and like a negative charge has that ability to kind of go both ways, either give away an H or accept an H plus. Water is an example of that as well. Water actually can work either way. Water can act as an acid in certain cases. It could also act as a base in certain cases. And water could even react with itself, which is essentially what happens when you have water. It's basically one's an acid, one's a base. So in this particular example here, what we have is this guy over here pretty much acting as the acid. He's actually, although the arrows look different than that, he's actually donating the H plus over here. And we're going to make our conjugate acid base pair here. So this is essentially what happens in water. In water, we have a good amount of these floating around in solution, H3O plus and OH minus. And again, one water acting as an acid and one acting obviously as a base. This sort of reaction is a equilibrium reaction, which means we actually can write an equilibrium constant for the autoionization of water. And if we do that, we get what is commonly referred to as Kw. Just like normal, when we would do our products over reactants, although they included it here, as they point out here, it is a constant and liquid, so we would not include it. And this gets reduced down to a really important relationship, which is known as Kw. So Kw is the water ionization product. It is the concentration of H plus times the concentration of OH minus, and it equals 1 times 10 to the minus 14. So that is almost like a constant, even though technically speaking, it would change with temperature because it is an equilibrium constant. But pretty much if you need the value for Kw, unless they specifically say we are not dealing with normal sort of temperature, 1 times 10 to the minus 14 is the value that you typically would use. Basically what this is H plus is the acid part of the solution, if you want to think about that way, right? OH minus is the base part of the solution, and use this relationship if you know one or the other. If you know the H plus concentration or you know the OH minus concentration, you could determine whether or not the solution is acidic, basic, or neutral based on which one is larger. So if we calculate the H plus concentration and it happens to equal the OH minus concentration, we would have a neutral solution, which basically means we have 1 times 10 to the minus 7 for the concentration of both of those guys. And basically they would equal each other out and be neutral. If we calculate the H plus concentration and it's larger than the OH minus concentration, basically what that means is the acid part is larger than the base part. So it would be an acidic solution. And lastly, if we calculate H plus and it's less than OH minus, that means that the hydroxide concentration is larger, which means really the basic part of the solution is larger than the acidic part of the solution, and it would be basic. Also a reminder, H plus and H3O plus is the same thing. So you will sometimes see this written as this. Again, basically the exact same thing, just H plus instead of H3O plus. So you will typically be given these concentrations, or at least one of these concentrations in problems. You need to make sure, obviously, in most cases, it will be a number in like scientific notation. So you want to definitely make sure that you use your exponent button correctly on your calculator when you push these in here. The comparison that you want to do, obviously, is the H plus concentration to the OH minus concentration to determine which one may be larger. So why don't we try one here? What is the OH minus concentration in an HCl solution whose hydrogen concentration is 1.3? And is it acidic, basic, or neutral? All right, so clearly here we would be using Kw, which is again the concentration of H plus times OH minus equals 1 times 10 to the minus 14. In this particular case, the hydrogen ion concentration is the H plus concentration. It's really the same calculation no matter which one you're solving for. In this case, OH minus would equal 1 times 10 to the minus 14. We will divide it by the H plus concentration of 1.3 and punching it in again, making sure to use your exponent button, 1 exponent button, negative button, and 14 would be the proper way to punch that in your calculator, by the way. That gets you a concentration of 7.7 times 10. Getting old, but I think that says minus 15. And because it is a concentration, we should have a molarity happening there, right? First off, any questions on that calculation? Yeah.
So you're always dividing these numbers?
For this particular equation? No, so it's always division. So when you rearrange Kw, when you rearrange this guy, if you wanted to solve for the H plus, you basically would be dividing the OH minus to the other side. So you would have 1 times 10 to the minus 14 divided by OH minus. So that's going to be division. And if you wanted to solve for the OH minus, you would be dividing the H plus to the other side, which also would mean you are dividing kind of like what we just did here in this particular problem. So this one is always, the good news about this one is always dividing. It's really the same formula no matter which one you're solving for. You basically take 1 times 10 to the minus 14 and divide it by whichever value they give you for the concentration. Other questions on that? Is this acidic, basic, or neutral? Yeah, it is acidic. We would be comparing the OH minus concentration to our H plus concentration. H plus concentration is larger and it is acidic, which I would hope, since it's an hydrochloric acid solution, that would be bad if it was basic, I imagine. So that does make sense. Yeah. You do, because HCl is a strong acid. So basically a solution, right, most of the time, especially like an acid solution, you know, the solvent is essentially water, right? So just the water itself has OH minus and H plus floating around. When you add the acid to it, basically in the process of making it, is going to contribute more H plus, which is why we see this concentration higher here than the OH minus concentration. Yeah. So it is in most cases, and for acids, it pretty much is. Water is usually the solvent that's used to make it, which is what you would use this for, basically. But we use it really for any solution, basically, because most solutions, like I said, is aqueous based, water based. So most solutions will have some type of concentration of each of those guys floating around in it, just because of the process of water being there reacting with itself. Other questions? Yeah. Yeah, I would. I probably won't. I mean, I probably won't give you a question per se like that, but you might come across a homework problem like that or something. So if you see in the homework problem, they specifically like point out like, hey, the temperature is not like 25 degrees Celsius, you know. They probably will give you the KW, or they'll point you to a table where you can maybe find the correct KW to use. So that is a really good question. Like I said, you know, I don't know if your textbook does it, but I taught one time with a textbook that would give questions like that. Like they would have you do this type of question, but go, hey, the temperature is like 19 degrees, and you had to go find the appropriate KW for 19 degrees. So remember that any K value that we come across pretty much this semester, no matter what the little symbol on the bottom is, KC, KP, KA, KW, KB, they're really all at the heart of it, equilibrium constants, which is basically what we talked about in the previous chapter, that really the one thing that can affect it is temperature. So regardless of the K, whatever the little guy is on the bottom, if really the temperature technically is not 25 degrees, you might have to go fish out what the correct K value would be for that. My guess, though, is in a book, they would probably lay up that number in the problem and want you to use it, would be my guess, or again, point you to a table. Other questions? Okay. That's good. They agree. Oh, that's good. All right, let's try this one here. A solution has an H plus concentration 1.2 times 10 to the minus 6. What is the OH minus concentration, and is it acidic, basic, or neutral? I imagine one of the right answers are up there, I would hope. Here we're given the H plus concentration of 1.2 times 10 to the minus 6. We're looking for the OH minus concentration. So again, as we just talked about, pretty much the same calculation regardless of which one you're solving for. The OH minus concentration would be 1 times 10 to the minus 14 divided by our H plus concentration, which would be 1.2 times 10 to the minus 6. Now, in this particular problem, it really didn't mention anything about temperature. So in that situation, it's safe to assume it's 25 degrees, and 1 times 10 to the minus 14 is really the correct value to use. When we do that, you end up with 8.3 times 10 to the minus 9 molar, or on your calculator, like most calculators, like 8 zeros. And an 8 because your calculator ran out of room. Yeah, so that's your calculators in scientific notation. You may get some answer that looks like that. Or if you put it in scientific notation, you'll get the 8.3 times 10 to the minus 9. Any questions on that calculation first off? Now we want to determine, is it acidic or basic or neutral? So we want to compare the H plus concentration to the OH minus concentration. And in this particular case, which one is larger? So in this particular case, it's actually the H plus concentration that is larger. And it's an important thing to remember that when you look at negative exponents, right, the smaller number is actually the larger number, because -6 means we're going 6 places this way and putting zeros. -9 means we're going even more places this way and putting zeros, which makes it actually a smaller number. So when you look at numbers written in scientific notation, if you have negative exponents, actually the smaller negative exponent is actually the larger number, because you're not putting as many zeros in front of it, and thus it becomes obviously a larger number. So in this case, it would be acidic, I believe here. Any questions on that one there? Now, another way that we commonly will measure acidity of a solution is pH. And pH runs the pH scale. And when we look at the pH scale actually runs from 0 to 7 to 14. Below 7 to 0 is acidic. Above 7 to 14 is basic. And technically speaking, dead on 7 is neutral. And that is because dead on 7 is when the concentration of H plus equals OH minus, which means they both will equal 1 times 10 to the minus 7 molar, which means if you calculate the pH, it's a pH of 7. So technically speaking, anything above 7, even slightly above 7, is slightly basic. Anything slightly below 7 is slightly acidic. We will make it very clear, dead on 7 is neutral, yes. Practical applications, some people call anywhere in that area maybe neutral, but just so there's no misunderstanding, if it's not 7, don't call it neutral. Yeah, so call it slightly acidic or slightly basic. That way I don't have to decide 7.2 where we stop calling it neutral and start calling it something else. So the real definition though technically is this, and technically the value actually is 7 when you calculate it, because those guys are equal to each other. To calculate the pH, by the way, 7 is sort of your midpoint. As you go from 7 closer to 0, you're becoming more acidic. And obviously, as you go from 7 towards 14, you're becoming more basic. That direction. To calculate the pH, we use this equation here. The pH is equal to minus the log of the H plus concentration. Again, you can substitute in the H3O plus there if you like. Same thing. Now let's talk about calculators for a second. If you have a display calculator, you should punch this equation in exactly the way it's written. you should use your negative button. You should use your log button. You should probably put the concentration in using your exponent button. If you have a non-display calculator, this equation and several others we're going to look at, you need to go backwards, which means you need to start with the number, then hit log, and then hit the negative. If you're not sure what type of calculator you have, which is probably the good question to ask, you hit log. And if it says log when you do that, congratulations, you have a display calculator. If it says error, congratulations, you have a non-display calculator. So display calculators, all the equations, pretty much the way they're written is how you should punch them in. If you, again, have more of a non-display calculator, you got to kind of go backwards on all these equations to correctly punch them in. Now, pH and significant figures is an important thing. So when we calculate the pH or a value like pH, the number of decimal places in the pH should equal the number of significant figures in the concentration value. So let's say, for example, here we had an H plus concentration of 1 times 10 to the minus 5 molar. Calculate the pH and see what you get. Calculate the pH to the correct number of digits. That is what your calculator spits out at you, a pH of 5. So that's the first step, right? You get a pH of 5, hopefully on your calculator when you do it. Should we write 5? Should we write 5.0? Should we write 5.00? Should we do 5.0000000? Nobody wants to go with this one? All right, it feels like a lot of zeros there. It felt like too many to start with. The correct pH as it is written here should be actually this one, 5.00. That is because the concentration value has how many significant figures? Has 2 significant figures. 2 significant figures means not how many significant figures my pH will have. It is how many decimal places, yeah? So concentration sig figs to decimal places. And by the way, we will talk about going the opposite way. You do the same thing going backwards. If you have 2 decimal places in your pH, your concentration should have 2 significant figures. So it goes both ways as you do it. So that's one that always ties people up. Again, it's sig figs to decimal places in this case, and obviously decimal places back to sig figs when we go backwards. Any questions on that? By the way, that is acidic, basic, or neutral. It is acidic. You should always look at the pH value to determine if it's acidic, basic, or neutral, because most everybody has this in their head, and that's always the value you should look at. When the pH goes up, the H plus concentration goes down. So the greater the H plus concentration, the lower the pH you will have, and vice versa. And that is because H plus concentration and OH minus concentration, they are really tied to one another through KW, and they're inversely related to each other, which means as the OH minus concentration goes up, the OH minus concentration goes down, and vice versa. As the OH minus concentration goes down, the H plus concentration will go up. So as one goes up, the other goes down, and they're related like that. And that means that as the H plus concentration goes down, technically speaking, the OH minus concentration goes up, which means technically you have more OH minus in your solution than H plus probably, and your pH should start to go up towards the basic side or heading in that direction, depending on how much you got going on there. Any questions on that? All right, so here again is the pH scale. There are also other similar scales to pH, but here are some things on the pH scale. Sodium hydroxide, which is obviously a strong base, up there by 14. Hydrochloric acid, which is a strong acid, down there by 1. Obviously, pure water here is 7. Vinegar and lemon juice and stomach acid, which is a version of HCl, those are all acids and acidic. By the way, if you take regular water and take the pH of it, will it actually be 7 in a lot of cases? No, it really won't. It probably will be like surprisingly like down in this range, depending on where your water is coming from, depending on how long you left your water sitting out in the air, because water and in the air, there's like CO2 that makes carbonic acid, which increases the H plus concentration in the water basically, and will actually lower the pH. Years ago when they used to do like those titration experiments everybody loves, yes? You used to have to boil your water and to get all the CO2 out of it before you actually made like your sodium hydroxide solution or any of those type of solutions. Nowadays they build better buildings, so they don't worry too much about it. But that's a very common thing. A similar scale to pH is one that's known as pOH, and as the name implies, it does measure the OH minus concentration. It's basically calculated the same way. It is minus the log of the OH minus concentration. That's sometimes really helpful because maybe you're given the OH minus concentration and you need the pH. So there really is a nice relationship between pH and pOH, that the pH plus the pOH equals 14. So it gives you a little bit of an option in terms of how you want to maybe solve some of these problems. For example, if you're given the OH minus, you could calculate the pOH, you could subtract 14, and you will have the pH value right there pretty quickly. If you're given the OH minus, you could still use KW and get the H plus concentration and put it into the pH formula. So there's a couple of different ways you can solve some of these problems, but you definitely should know that pH plus the pOH equals 14. You should know how to calculate the pOH, and clearly you should know how to calculate the pH as well. Now, this is also where people screw up because they calculate the pH, they calculate the pOH, and they decide, well, my pH was above 7, so it's basic, but my pOH was below 7, so it's acidic. So the same solution is both acidic and basic at the same time. Doesn't happen, yes. So if you're asked that question, is it acidic, basic, or neutral? Only one answer should be given. It should either be acidic, basic, or neutral. It cannot be acidic or basic at the same time. And that sometimes happens because people do calculate the pOH and the pH and look at both numbers and give basically both answers. So don't do that, yes, for sure. Also really important to look at the pH value to determine if it's acidic, basic, or neutral, because the pOH scale runs opposite of the pH scale, which means if you have a high pH, you have a low pOH. And if you have a low pH, you have a high pOH. They are opposite scales. So like I said before on the previous slide, most people have the pH scale in their head. So always look at this guy when you're trying to determine if it's acidic, basic, or neutral, and you probably won't screw up. Any questions on that there? By the way, there's a couple other things that's important that we could calculate here, and that is we could actually, if we are given the pH or if we're given the pOH, we could actually calculate the concentration. So let me just find somewhere to scribble here. Yeah. I'll scribble right here in the middle, I think. There we go. So if we are given, yeah, I can get one more maybe. There we go. So if we are given the H plus concentration from it, and we could calculate the H plus concentration by taking the inverse log of the minus pH. Now you may be asking, what is the inverse log? For a lot of you, it is how you put things in scientific notation in your calculator incorrectly. This is actually where you use that button. This is on your calculator, top left corner, usually shift second button, and this is the log button with the 10 and the X above it. That's actually what you should use it for. That's the inverse log. When you do that, it typically will pop up a 10 and a caret on most people's calculator. And then you want to make sure you do a negative pH on that. And that will give you the H plus concentration. And if you have the POH, you could get the OH minus concentration from it. It is the exact same calculation. It is the inverse log of the minus POH. Again, your second button or shift button, usually on most calculators, gives you a 10 and a caret minus POH. So this again gives you a variety of options. If you have the pH or POH, you could go directly and get the H plus or OH minus from it. Obviously, you could use all the other ones that we talked about. So we'll just put them all here on the same page. Our H plus concentration, our POH minus the log of the OH minus concentration, pH plus POH equals 14. And lastly, not to forget, our KW still works perfectly fine in some situations if you like to use it. 1 times 10 to the minus 14. The page of acid equations there. Yes, any questions on any of those there? As you can see, like I said, there is a variety of ways you can solve the same problem. There's no real right way. It's whichever way you want to do it. You really should get the same answer regardless, as long as you choose a correct pathway. Like I said, if you have the OH minus, you may just want to get the POH directly and get the pH that way, or you may want to use KW to get the H plus and go into the pH. Do you have a question or? What's that? That's the inverse of IN, like inverse of the inverse of the log. Yeah. So on most people's calculator is the log button. Above it, there's like a 10 and an X, and that is usually your inverse log button. On my particular calculator here, it is right above the log button, and it's a 10 to the X, and that is the button that you want to use. There is a calculator that has a dedicated button. Some of them do, but most it's on the log button is usually where you'll find it. And it's not, you might, it's not the natural log. So you don't want to use the actual natural log button. You want to make sure you're using the inverse of log. It's the inverse log. Natural log is something else we'll use a little later on, but natural log is a different function. So it's actually kind of like the, reciprocal there of the regular base log 10 is basically what it is. So you want to make sure you're using that one, not the LN button. That's something different. The LN button will have an E above it, and we'll use that E in a future calculation. That's a totally different button. You should have an LOG button that's got the 10 to the X above it, and that's the one you want to use. It's got to be negative. So again, not subtract. So make sure you're actually using your negative button, to do that. Yeah. And that will spit you out the H plus concentration if you started with the pH, or the OH minus concentration if you started with the POH. Question or? Yeah. And that's, I put this here because on most people's calculators, when you hit that button, that's usually what kind of pops up. When you kind of actually hit that button, that's sort of what pops up. And then you want to make sure you do a negative of the pH or POH. All right, why don't we try some here so we can use our buttons, make sure our calculators work. All right, so pH of rainwater is collected is 4.82. Let's just do everything to make sure our calculator works. So let's calculate the POH. Let's calculate the H plus. Let's calculate the OH minus. And let's decide, is it acidic, basic, or neutral? And the bottom one, we have the OH minus concentration. So let's calculate the H plus. Let's calculate the pH. Let's calculate the POH and decide, is it acidic, basic, or neutral? All right, so take a couple minutes, play with your calculator, make sure it's all working correctly. It's a pH of 4.82. So really with a pH of 4.82, since we decided we're going to solve for everything, we really have two options as to what we could get really pretty quickly. We could obviously get the POH, And we could also get the H plus concentration directly from it. By the way, the name tells you what you could get from it, and it also tells you what you need to calculate it. So pH means you could get the H plus concentration if you have it. If you want to calculate the pH, you need the H plus concentration to calculate. So we'll start with, we'll do the H plus concentration here since we just talked about it. The H plus concentration will equal the inverse log of the minus pH. So again, on your calculator, it will look something like a 10 a carat. We want to make it negative 4.82. And if we do that, we end up with negative 4.82. We end up with an H plus concentration of 1.5 times 10 to the 1, 2, 3, 4, 5, negative 5. I hope if I counted that right. We do need a molarity as it is a concentration on that. Any questions on that one there? Yeah, so let's talk sig figs is a good question. So we're actually going the opposite way what we talked about, right? So our pH value started with how many decimal places? Which means the concentration should end up with 2 significant figures, yeah? So remember, go sig figs to decimal places. So in this case, 2 decimal places should tell us that our original concentration had 2 significant figures in this case. If it did have 3 significant figures, we would see 3 decimal places on the pH value. No. Other questions on that? Okay. Now, again, at this point, you now have some more options. We have H plus, which means we could dump it into KW if we wanted to, right? To get the OH minus concentration. Or I could still get my POH. So I'm going to do that. I'm going to get my POH, which again, the pH plus the POH equals 14, which means that the POH would be 14 minus the pH, which is 4.82. That's going to give me a POH of 9.18 as my POH. Any questions on that? Now I gave myself 2 more options. I can do the inverse log of the negative POH, right, to get to the OH minus concentration. Or if you're more comfortable, you can still use KW to get the OH minus concentration. Since it's kind of a newer calculation, we will do the same thing that we did for the H plus here. So I'm just going to kind of come over here on the bottom-ish. My OH minus will be the inverse log of the minus POH, which for the guy up on top would again be a 10 and a carat minus 9.18. And that's going to give us, I got that, there we go. That. Looks like, again, we will get here 6.6 times 10 to the negative 10. Again, molar would be needed in this case. Same thing in terms of sig figs here. Our 9.18 has 2 decimal places, translating to 2 significant figures in the concentration. Now, all that is left is to decide, is it acidic, basic, or neutral? And it is. It is acidic. Frankly, the easiest way to determine that would be just to look here, right? And that is obviously less than 7, which means that this solution is acidic. Any questions on any of those calculations? Yes?
Does POH have
It doesn't. So pH, POH are just numbers, no units associated with it. But remember, if you do calculate any type of concentration, it should match the original concentration unit, but in most cases it will be molarity. So you should put the molarity or the big M for those guys that are concentration. So other questions? All right, so let's take a look at the bottom here. Again, in this particular case, we are given the OH minus concentration to start with. So really from that, again, you have 2 options. You could use KW if you wanted the H plus, or you could go right into the POH here to calculate the POH. So that's what I'm going to do. I'm going to calculate the POH first, which will be minus the log of the OH minus, which in this case is 2.5 times 10 to the minus 7. That's going to give me a POH here of looks like 6.60 looks like on our POH. We then can very simply get the pH by simply subtracting it from 14. So might as well just do that part. That's pretty straightforward. pH would be 14 minus the POH. So that's going to be 14 minus 6.60. That is going to give us a pH here of looks like 7.40. Let's see, we got POH, we got pH. All this left now is H plus. And again, if you wanted to, for old time's sake, you can use KW. So you could just do H plus is equal to 1 times 10 to the minus 14 divided by our 2.5 times 10 to the minus 7. Seems to fit nicely in that hole on the screen there. So 1 to the minus 14 divided by 2.5 to the minus 7. Gonna give me a 4 as it cuts off on my calculator. There might be more digits, so I'm just gonna call it 4.0 times 10 to a lot there. I think that's 8, maybe 1, 2, 3, 4, 5, 6, 7, 8 minus 8 molar. And again, you should get that same answer if you did the inverse log of the minus 7.4. You should pretty much get the exact same answer if you did it that way. Yes. You got, I'm sorry? Where's the? Yeah, well, I get it. I rounded off on my calculator. Probably if I had a scientific notation, it would probably be 3 point something, to be honest with you. But limitation of where I could go with that. But yeah. Other questions on that? So again, you do have multiple ways. By the way, this is acidic, basic, or neutral. This one would be. This one would technically would be slightly basic. Yeah, just above 7 there. And looking at the pH value here, obviously, is what we want to look at now. Other questions on that there? Questions on any of those calculations? Hopefully you're finding the right ones to use. All right, let's see. All right, let's try another one here. Practice one more time. Pretty much we want to determine everything, and while we're at it, is it acidic, basic, or neutral? Let's add that in. So we have the H plus concentration. Again, you could either get the OH minus concentration, you could get the pH from it. I'm going to start with the pH. So we'll do pH equals minus the log of the H plus concentration, which in this case is 3.5 times 10 to the minus 6. And that gives us an opening pH here of something. 3.5 minus 6. Well, it looks like we'll go with 5.46 as our pH. Since we have the pH, might as well just subtract 14 or subtract it from 14 to get the POH. That's a pretty simple move. So that's going to give us 14 minus the pH, which is 5.46. And we'll do a little bit of that and get an 8.54. At this point, all this left is the OH minus concentration. So why not? We got the POH here. So OH minus concentration will equal the inverse log of the minus POH. So again, I'll count on your calculator, a 10, a caret will probably pop up. Make sure you make it negative 8.54. And we will end up with, where did that thing go? Right there. Again, my calculator is cutting off, so I'm just going to call it 2.0 times 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, I believe, if I did not mess that up. Again, if you're maybe in scientific notation, which this calculator does not do, actually, you know, you might have maybe a slightly different number, 1 point something or something like that. In this case, acidic, basic, or neutral. Should be acidic, again, based off of our pH value there. Any question on any of these calculations? Yes. What's up? Did you? Let me try this one more time here. We got minus 8.54. You got, what'd you get? 2 point times 10 to the minus 9? Okay. It might be, again, my calculator can't, I just ran out of digits on my calculator, so I'll trust it. We're gonna try it the other way and see, but should have brought a better calculator to this game here. All right, 3.5 to the minus 5. Yeah, okay, so if we go that way, it is probably like 2.9 to the minus 10. Is that what you guys got? No. You can. Yeah, no, I'm sorry. I hit the wrong number. I got the same. Yeah, I'll trust you because my calculator dies at that number. So 2-ish times 10 to the minus 9. You have a nice calculator that you could put it in scientific notation. You could get the more digits. I clearly, honestly lost my good calculator. I still can't find it. So I'm working with, this one here. All right. Any questions on that? So, but it should be to the minus 9, obviously, right? Yep. Okay. Question on any of these calculations here. Okay. So clearly you need to know how to do all these calculations if they are asked of you. So let's talk a little bit about the strong electrolytes here. Strong electrolytes are, well, electrolytes in general are things that when they do dissolve in solution, as we talked about, break apart into ions. They're able to conduct electricity, and strong electrolytes 100% break apart in solution. And what that means is you no longer have any of the kind of whole units together. So for example, if you have sodium chloride that you dissolved in water, when it's dissolved in water, you no longer have any sodium and chloride units still together. It has 100% broken apart into ions of the sodium ions that are floating around and the chloride ions that are floating around in that solution. Now we have weak electrolytes. Weak electrolytes, as we sort of talked about a little bit in the previous chapter as well, they are barely reversible sort of reactions, if you will. They pretty much will stay together and they will break apart a little bit. So they'll produce a little bit of ions in solution, which is why they're still considered an electrolyte, but they will not produce anywhere near the amount of ions in solution as a strong electrolyte. So strong acids are strong electrolytes. Strong bases are also strong electrolytes. Weak acids and weak bases are also weak electrolytes as well. When we look at this is acetic acid, vinegar, basically. So in solution of acetic acid, you pretty much mainly have the whole thing still together. We'll produce a little of these guys, but not as much as, say, our first guy here, which is hydrochloric acid. It will produce H3O plus and Cl minus. This is nitric acid, which is another strong acid. Will also produce H3O plus and nitrate. That's perchloric acid, also a strong acid, H3O plus and perchlorate. And that's sulfuric acid, which will produce obviously H3O plus and some HSO4 minus in this particular case. In these cases, these are all strong acids, which means 100% of what you got going on are the ions on the right-hand side. And they are strong acids because they completely break apart. And what makes something an acid is the ability to produce H3O plus, yes, or H plus. So they're able to produce a lot of H plus really quickly in solution. And if the concentration of H plus goes up really quickly in solution, what will happen to the pH? Will start to go down, right? It should become acidic. You'll probably have a larger concentration of H plus than OH minus when you do that. And that is why when you have a solution of a strong acid, the pH is less than 7 in that particular case, because you have more H plus than OH minus in the solution. HCl, nitric acid, perchloric acid, sulfuric acid, hydrobromic acid is a strong acid. Hydroiodic acid, also a strong acid. That list there is a good list to keep in mind. These are strong acids, so you come across them, you understand that they are really strong acids in this particular case, which makes it easier to identify perhaps weak acids because they're not one of these guys, basically. And that's a good indication that you're maybe dealing with a weak acid, which we have some here. Weak acids are weak electrolytes. So these are some weak acids. We have hydrofluoric acid, we have nitrous acid. Same thing happens here. This guy will produce H3O plus some F minus. Guy will produce H3O plus some nitrite. A little H3O plus some sulfate. And this will produce H3O plus and some hydroxide. Okay. Different here, these are weak electrolytes, which means when you have a solution of these, this is mainly what you got going on. And you have a little of these guys basically in solution. That is the difference between a weak acid and a strong acid. A weak acid will mainly stay together, but it will still produce some H plus ions in solution, which meets the definition of an acid, but is nowhere near obviously the amount of H plus that would be produced if you use hydrochloric acid versus hydrofluoric acid. Hydrochloric acid, all you have to do is dump it in there and you're just going to generate a lot of H plus. Hydrofluoric acid, when you dump it in there, you're going to generate not as much H plus because it's going to mainly kind of stay together as it's floating around. Any questions on that there? Strong bases, on the other hand, are just like strong electrolytes or strong acids. They 100% break apart. As I think we talked about maybe the other day, that is basically group 1 and 2 on your periodic table there. If you start with sodium and go down to potassium, hang a right at calcium, go down to strontium and barium, you know, those are a lot of your strong bases. Put hydroxide on all those guys, you get potassium hydroxide, sodium hydroxide, calcium hydroxide. These are all typically strong bases. And as we talked about, group 2 is the alkaline earth metals. Alkaline means basic. So that's where a lot of our strong bases come from. So just like our strong acids, each of these guys produce hydroxide, which makes some bases. You get a lot of hydroxide in solution very quickly, which means the pH should go which way? Should go up, right? pH goes up because OH minus went up and H plus went down, right? So you have more OH minus. So like our acids, 100% of what you got going on in solution is on the right-hand side here. You have no sodium hydroxide units still together in solution. And again, much like the acids, it's able to produce a lot of hydroxide really quickly, which makes it a strong base. There are definitely some weak bases as well. F minus, for example, is a weak base. When it reacts with water, it will produce hydrofluoric acid, where it comes from, believe it or not, and it will produce some hydroxide. going to kind of go this way, the H plus. We're going to produce some nitrous acid and some hydroxide. So again, these guys are able to produce hydroxide, which again makes them a classification of a base. But in solution, mainly going to kind of hang out over here on the left-hand side. So not going to produce as much free OH minus, and thus not going to be as strong of a base as sodium hydroxide, which essentially just needs to go for a swim and is going to break apart 100% and produce a lot of hydroxide. So there is a couple of important relationships that's going to help a little later on in this chapter. So let's talk about the relationship between a strong acid and its partner, which would be its conjugate base, or a strong base and its conjugate acid. It is a opposite relationship, which means if you have a conjugate acid or conjugate base that comes from a strong acid or a strong base, these guys are essentially super weak. Yeah. So if the partner came from something that was strong, it's going to be relatively weak, and vice versa. If you have a conjugate acid or a conjugate base that comes from a weak acid or base or weak base, these guys will be relatively strong. So there's sort of an opposite relationship of what is produced as a result of where it started from. Anything that derived from a weak acid or weak base will be relatively strong. Why is that important? Well, it's important because those guys in solution with water will decide to continue to react, and they will continue to react and affect the pH of that solution. If you have something that comes from a strong acid or strong base, it is relatively weak, which means it's not going to continue to react. It will really have kind of no effect on the pH in sense of changing it or anything like that. That occurs when we're going to talk about salts a little bit later on in this chapter. But that relationship, that sort of opposite relationship, is a really important one to remember. Again, comes from anything that's strong, its partner is going to be relatively weak. If it comes from anything weak, the partner will be relatively strong and continue to react. Any questions on that there? Here's a table. You have a similar table in your book, but again, our strong acids and strong base, there's an opposite relationship going up this way, stronger acids and weaker bases, or stronger bases going down the opposite way. That's very common here. Here again, visually, strong acid like HCl in solution, pretty much all ions present. No guys still together. And as you can see with our weak acid, still mainly stays together, but a little bit of those ions are formed, which does make it a weak acid. Now, not always will you be given just a generic H plus or OH minus. You may be asked to calculate the pH of a strong acid or strong base. Because it is a strong acid or strong base, you could figure out the appropriate H plus and OH minus concentration because it 100% breaks apart, right? So why don't you try that on these, calculate the pH of each of these and see what you come up with. Take a look. So first off, we see nitric acid, not the generic H plus or OH minus given to us. We should recognize that nitric acid is a strong acid, which basically means that when it is in solution, it is going to 100% break apart into H plus and NO3 minus, right? And again, 100% of what you got going on should be what's over here. Now, important to calculate the pH is clearly the H plus concentration, right? So if we are given that the nitric acid is 2 times 10 to the minus 3 molar, what would the H plus concentration be? It is a 1-to-1 relationship, right? Which means concentration works that way. If it's a 1-to-1 relationship, this will be 2 times 10 to the minus 3 molar. By the way, the nitrate is also a 1-to-1 relationship, which means the nitrate would be 2 times 10 to the minus 3 molar. Not that you really need that for this problem. Because it is a strong acid, and this is 100% what we have in solution, we actually could calculate the H plus concentration by looking at the molarity. And that means we have what we need to go into our pH equation. And if we do that, we get minus the log of 2 times 10 to the minus 3. And that is 2.7 in terms of the pH, which does make sense because it's acidic. So perhaps you learned last semester concentrations, how they work, yes, but if in case you didn't, basically the simple way is it breaks apart into a 1-to-1 relationship. It's the same concentration, breaks apart into a 1-to-2 relationship. You multiply the concentration by 2, 1-to-3, multiply it by 3, and so forth, right? So that's important here, as barium hydroxide is a strong base. When it breaks apart, is going to 100% break apart into barium that has a +2 charge, and you get a couple of hydroxides in this case. The 2 comes out to the front. That's important because in this case, to get us to the pH, we actually need the OH minus concentration, so we could calculate the pOH. That means that the barium hydroxide is 1.8 times 10 to the minus 2 molar. It is a 1-to-2 relationship for the hydroxide, which means you do need to multiply that number by 2 to get the correct hydroxide concentration in that solution. And that would be 2 times 1.8 to the minus 2, gets you an actual concentration of 0.036 molar for your OH minus. That is the correct one that should go into your pOH, which will be minus the log of 0.036. And that gets you, call it a 1.44 for the pOH. If by some chance you thought that was the pH, that should not make sense to you, right? Because that would technically be an acidic pH. So you will take the pH is equal to 14 minus the pOH, gives you 14 minus 1.44, and that gets you like a, if you subtract it from 14 and not 12, let's try that again. You get a 12.56, which should make sense because that is a basic pH, and what the correct one should be. Yeah.
Let's just say like when physics class, like what if you're like close? It's like, what if I got 12.26? Like, would that be right?
It would probably be wrong if you're kind of that far off, I would think. Yeah. So, you know, you should be fairly close if you do it correctly. You know, it shouldn't be super far off. Yeah. So you either maybe, and you shouldn't be doing too much rounding here anyways, you know, so you want to avoid doing a lot of rounding. It's sort of magnified when you're doing logs and stuff like that. So try not to do a lot of rounding on this stuff until kind of the end and clean it up. Otherwise, if you do a lot of rounding, especially with the logs, the inverse logs, is just going to sort of magnify your rounding, and you may find yourself kind of far away. So as long as you don't do any like weird extreme rounding, you know, you really should, you know, be fairly close, you know. You know it, I'm sorry, you know it should be, yeah, it definitely should be, it definitely should be basic because obviously it's a base, just like the first one obviously should have an acidic pH because, you know, it's an acid. And those are good things to keep in mind as you're doing these calculations. You know, again, you know, it's common, sometimes people will circle this guy and go, that's like my pH. And, you know, if you just think about it, it shouldn't make sense, obviously, because it's a base. Any questions on that? By the way, just one point on the concentrations here. just so we're clear as to, you know, sort of what is going on. Technically, if this was, say, the 1.2 times 10 to the minus 5 molar, that is moles per liter of barium hydroxide. And what we would do is a basic mole to mole relationship where there is 1 mole of barium hydroxide, 2 moles of hydroxide. The barium hydroxide cancels, and now you have moles per liter of hydroxide. Ultimately, we multiply by 2. That's the long version of multiplying by 2. It's really stoichiometry is what we're doing there to move the concentration to where we need, just so you understand that, hopefully. Any questions on any of that stuff there? All right, we will clearly lay it up there.